So far, this hasn't been processing too terribly slowly since we've only been using 10 cutters, but we'll often need to use far more cutters than this and perhaps higher mesh resolution as well. In my setup, I use two different trimming options. One will trim to the bounding box of our input geometry, and one will trim more precisely to that input geometry with all of its concavity and holes. Now to set up the bound trimming option, let's create a new bound SOP. We could use the bound SOP that we used at the beginning of our setup, but I like to use a separate one so that I can expand the boundary a little bit. Let's rename this new bound to bound expand and display that. And then we'll increase both the lower padding and upper padding a bit to add some buffer on the edges of our input. And as I've mentioned already, you could use your initial input bound for this, but if you start changing the padding on that input bound, it'll change the results of your scatter and your noise and etc. And it's very helpful to be able to change the padding trim without changing the actual generated cutters themselves. Now with previous versions of this tool, I used a series of clip nodes to clip our input based on our bound here. If you drop in a clip node and connect the cutters to that and display it, and perhaps change the Z direction to 1, you'll see that this clip SOP is defining a plane and a direction and creating a perfect cut line and keeping either the primitives above or below that. Now the clip SOP is really fast and reliable. It's much faster than the Boolean SOP and less likely to break because it's not nearly as sensitive to its input. But it's a little bit more annoying to set up because you would have to use 6 of these for each of the negative and positive X, Y, and Z axes. And each of those clip SOPs would have to use a B-box lookup to our bound expand here to determine what clipping planes to use. Now because that's more annoying to set up, I'm just going to stick with simple geometry grouping. If you drop in a group SOP and connect our noisy cutters to that, and then connect our bound expand to the second input of the group, we can change the group name to something more intuitive like trim area, and turn off the base group, turn on bounding regions, and select bounding object. And this bounding object grouping only works on points or vertices, so let's change that group type to points. And of course rename our group SOP to keep things nice and clean. Now if you display that group, you can see some of those points that it's selected in there. It's a little bit hard to see all of those points within that mass of cutters. But if we create a blast SOP and select that trim area group and display that blast and flip it to delete non-selected, then you can see exactly the areas that this is grouped. Let's rename our blast node to keep things clean. And then one more little step I like to add is to promote this group from points to primitives. We can right click on that group trim area output, type in group, and select group promote, drop that in between them, and then select trim area from this group drop down and switch this convert from to convert it to primitives. And because we're not selecting this include only elements entirely contained option, then our selection will expand a little bit so that any primitive containing a point that's been grouped will be selected in our promoted group. And of course rename our promote to keep things nice and clean, and we now have a nicely optimized cutter area. One additional tweak that we can make to our setup to optimize the distribution of cutters and how it's trimmed is to use an oriented bounding box instead of just a plain bounding box. Here I've used a couple clip nodes to chop out a diagonal slice from this building geometry, and you can see that if we look at the bounds, this bounding box has a lot of wasted space in it since by default that is going to find the maximum point in all 3 axes. On this bound node though, if you turn on this oriented bounding box option, then that will optimize every step of the process. You'll get your scattered points only lying within that real region of the geometry, And of course our cutter planes are still far larger than they need to be, but if we use an oriented bounding box on our expanded version as well, that will help to optimize that trimming so that it has less wasted geometry in there. Now, I always leave this bounding trim on since this method generates so much excess geometry around the sides, but you can see there's a lot of wasted geometry in the center here that won't be cutting through the building walls or anything. However, I don't always want to remove that much extra because it can be really helpful to move these cutter planes around after they're generated. We can use the connectivity class information that we used for our cutter noise offsets to select specific cutters. Now, because we'll be bundling this whole setup into a reusable HDA, I like to keep everything nice and cleanly named. So instead of just using an attribute called class, let's call this cutter ID instead. So on connectivity, we'll rename the attribute. And because this attribute wrangle uses the name class, we'll have to change it there as well so that we don't break our offset expression. Let's go back to the bottom just to make sure we didn't break anything by changing that attribute name. Cool, everything still looks good. Now if we go to our selection tool by hitting S and then use this little button or the number 9 to bring up the select groups or connected geometry option, you can go to this little gear icon here to select by any attribute on your geometry. Now you'll see that the attribute we want is not coming up under primitives since that class attribute is a point attribute. And ultimately we will want to have this exported as a primitive attribute from our setup, so we can use an attribute promote at the end here and display that. Select the cutter ID attribute and make the new class primitive. So now when we go to this little gear icon, you'll see that cutter ID pop up under the attributes that we can select by. So now with cutter ID specified, you can pick any of these cutters in our geometry here, perhaps this one, and then if you tab in the viewport and start typing transform and hit enter, that will automatically populate the group parameter of the transform node with what you've selected in the viewport. And now we can move this cutter around. Say we want to chop off specifically a section from this corner here. We can move this and rotate it and etc. And this is a nice way to combine some purely procedural with manually driven art direction decisions. Alright, so let's delete that transform node and take a look at doing that more accurate volume-based trimming that we can use anytime that we're not trying to grab these larger intact cutter planes. So let's start by creating a VDB from polygons node. And then we'll connect that all the way up to our input geometry. And you have to be a bit careful when you create VDBs because it uses this voxel size to determine the resolution of the volume. So if you have a very large object, you could accidentally create a super high res volume that will waste some of your processing power. And it can be a bit slow as well. So let's start with a value of 1 here and see what that looks like. That looks like that'll be good enough for now. This doesn't have to be a very detailed volume since we're just using this to select the points that we want to keep as our cutter geometry. Now with this volume-based trimming, we still want to give ourselves a little bit of buffer area around the object. So let's create a VDB reshape node, hook it up to that VDB from polygons, and you'll see by default that dilates this out a little bit, which means it expands it. We can expand that a little bit more, and when we make an HDA for this, we'll want to add a control to determine how much we're expanding this volume. This looks like this will work as a good starting point. So we can copy the same grouping and blasting nodes that we used for our bounding based trimming. Let's just copy that, bring it down here, and paste it again. Maybe just to keep things clean, I'll drag out our attribute promote for that cutter ID to save it for the very end of our network. And now let's take the output of our bounding trim blast and connect that to the group node that we're using to trim based on this smaller volume. And we can connect our VDB that we've expanded to that group trim area and display that. And even though we're selecting based on a volume in this case, it looks like the group bounding by object works with an SDF input, but because that's a volume, I typically still switch this to use a bounding volume, but I guess for an SDF it doesn't really matter. If you're using a fog volume instead, then it probably would be more picky and require you to use the bounding volume type there. So now that we're grouping the points that are near the geometry, we can leave the group promote and blast as they are and display the end of that. And you can see now we have some nice optimized cutters that'll be much lower resolution and a lot faster for our Boolean fracture to process. Now, I used to apply both of these types of trimming after the low frequency noise was applied, and it's very important to do that after the low frequency and not before, because if you apply it here, when the noise is applied, it can push geometry in or out of that bounding box. And in the past, I have applied that trimming at this stage before the low frequency noise because the subdivide can be pretty slow when you have heavy geometry. Once we're running a whole lot more cutters, we probably won't want to subdivide them all. So for now, I'm going to pull out that subdivide and mountain, and I'll bring them down to the bottom of the network. But this can be slightly risky because if this mountain pushes our geometry in or out of the actual object, then that could result in some of these partial cuts that I've mentioned previously are problematic, where our cutter plane kind of goes into and stops somewhere within the bounds of that actual mesh. It's usually not a big problem because you want to be giving yourself a decent amount of buffer with this reshape anyway. You can always increase that if you find yourself running into that problem. But it's still an issue that can arise pretty easily, and I've chosen to just watch out for that problem when doing my fractures rather than slowing down this whole process by doing the subdivide and fine mountain before the trimming. Now to finish up this trimming process, let's delete that group that we're using, this trim area here, because it's always good to remove any unnecessary attributes and groups because that data all needs to be tracked on that mesh. And some of those groups and attributes, if left on our cutter geometry, might be transferred onto our actual fractured geo, so we want to make sure that we don't have anything existing on our cutter geometry that we won't need later. So here I'll just drop in a group delete, put that right after our last blast trim area. And you could just use a star to delete all the groups on it, or you can just use this drop down to select only that trim area. And you can see we also still have this offset attribute from when we set up that low frequency noise. So we can just go up to that noise portion of the setup and drop in an attribute delete to get rid of that offset attribute. So now let's go to the very bottom of our network and reattach this attribute promote for that cutter ID, which we are going to leave on the geometry. And actually, when we make our HDA, we'll create an option for whether you want this to be exported or not, just so the user can decide if they want to keep the geometry extra clean or if they want that available for moving those cutters around.